Hi kids, now we'll be going with this elastic collision question. So I have taken simple values for easy calculation. There is a point mass of mass m and there is a rod of mass m and rod length is L. This point mass is moving with the initial velocity u. This is on the horizontal plane. So you don't have to bother about like weight pulling this way, right? And frictionless surface. So this guy is going to go and it is going to hit, and this is perfectly elastic collision. Now what will happen? On the rod there will be force in this direction, so center of mass of the rod will be moving and rod will be rotating about the center of mass also. So what I am doing is I am visualizing rod's motion as after collision rod will be having some velocity, that is velocity of center of mass of the rod, or about center of mass there will be rotation, or instead of center of mass you can say like rod's motion can be visualized as motion of one point and motion about that point. So that point I am taking as center of the rod for time being. Okay, so this is before collision. This is having velocity u, it is colliding. After collision this velocity is v, this angular velocity is omega. Then this point velocity on the rod will have motion off center and motion about center, that is v plus L by 2 omega, motion of the point plus motion about the point. Now this point is having velocity v plus L by 2 omega, velocity of approach is u, so velocity of separation must be u, so this guy's velocity will be v plus L by 2 omega minus u. So I have put E equals to 1 in the figure itself. Now apart from that, all the forces are internal forces during collision, so I can do conservation of momentum, and all the forces are internal forces during collision, so I can do conservation of angular momentum also, because torque due to internal forces will be 0. So I can do conservation of momentum, I can do conservation of angular momentum. So let me go with conservation of momentum first. What is the initial momentum of this guy? M into u. This guy is 0. So initial momentum is m into u. Final momentum of this guy is m into v plus L by 2 omega minus u. M into v plus L by 2 omega minus u. This is the final momentum of this guy, and final momentum of this guy is m into v. That's how you will be doing conservation of momentum. Initial momentum equals to final momentum. From here, when you modify, I got one equation, but there are two unknowns here. So I need to write one more equation. That other equation is going to be conservation of angular momentum. Now I said conservation of angular momentum can be done about any point. So what we will do, we will choose this point first, P. Now when I choose point P or some other point in the space, angular momentum must be conserved. So what is the initial angular momentum of the system? That is angular momentum of the point plus angular momentum of the rigid body. Angular momentum of the point is 0 because that velocity is passing through this point. So angular momentum of LO thing is 0. Now for a rod there will always be two components for easy calculation: angular momentum of center of mass and angular momentum about center of mass. Angular momentum of center of mass is 0, angular momentum about center of mass is 0. Initial angular momentum for the system is 0. Finally this guy is moving with some velocity, still his angular momentum will be 0 because his velocity is along the line, right? So angular momentum of this point after collision is also 0. Now for rod there will be two components: angular momentum of center of mass, angular momentum about center of mass. Angular momentum of center of mass will be perpendicular distance into mv. I have taken this direction positive for time being. So angular momentum of center of mass and angular momentum about center of mass will be IC into omega. This is in the opposite direction. Angular momentum of center of mass, angular momentum about center of mass. Initial angular momentum of the system equals to final angular momentum of the system. This is for point, this is for the rod. This is for the point, this is for the rod. So when I modified this equation, I will be getting very good relation here. This is from conservation of angular momentum. So we got two equations. One is this equation using conservation of momentum, one is this equation using conservation of angular momentum. L omega is 6v, I just substituted it here and I got v as 2u by 5. Now once I substitute it here, then I will be getting omega as 2l by 5 u by L. Right. Now we will try to see how to do conservation of angular momentum about other point. So suppose if I don't want to take conservation of angular momentum about point P, I am taking this point as Q. Now initial angular momentum of the system is, for this guy, perpendicular distance is L by 2. So L by 2 into mu, I have taken this direction as positive for timing. Angular momentum of this guy is this much, and angular momentum of the rod, angular momentum of center of mass and about center of mass, both are 0. I didn't put it here. Now angular momentum of this guy after collision is perpendicular distance into m into his velocity. This is the angular momentum of this guy, and this direction is positive we have taken. Now angular momentum of center of mass will have angular momentum of the rod will have two components, angular momentum of center of mass and angular momentum about center of mass. Angular momentum of center of mass is 0 because it is velocity is passing through that point. Angular momentum of center of mass is 0. Angular momentum about center of mass is ml square by 12 into omega IC into omega. Now, initial angular momentum of the rod is 0. This is the angular momentum of this guy. So, initial angular momentum is this much. This is the final angular momentum of point mass. This is the final angular momentum of the rod. Angular momentum of the rod will have two components, of center of mass and about center of mass. Now, when I manipulate it, I got this relation. This is from conservation of angular momentum. Conservation of momentum we should be doing. This is from conservation of momentum. This is from conservation of angular momentum about point Q. I solved these two equations and I will be getting the same results. Now, I will do conservation of angular momentum from other point. So, I am taking this point R. Initial angular momentum of the system is L into mu. I am taking this direction as positive. For rod it will be 0. Final angular momentum of the system will be point mass plus rigid body thing. So, for this guy angular momentum is perpendicular distance L into m into his own velocity, and for rod there will be two components, angular momentum of center of mass, angular momentum about center of mass. Angular momentum of center of mass will be given by L by 2 into mv, that is in this direction, and IC into omega is also in the same direction. So, both are positive, IC into omega. Angular momentum initially equals to angular momentum finally. Angular momentum finally consists of angular momentum of the point and angular momentum of the rod. Angular momentum of the rod will have two components, angular momentum of center of mass and angular momentum about center of mass. When I do the manipulation, I got this result. Now, this is from conservation of momentum, this is from conservation of angular momentum about point r. When I solved these two equations, I am getting the same results. So, that is how we approach for conservation elastic collisions, but you can clearly see these calculations are little difficult, but calculations turned out to be much easy when I take conservation of angular momentum about point P. The reason is initial angular momentum is 0, finally also this guy's angular momentum is 0. In fact, if it is elastic collision, if I take conservation of angular momentum over this point, no matter what is the question, I will be getting similar result, right? Anyway, we will try to see it in a slightly different way. Now, we will observe the entire situation from a frame moving with velocity u by 2, that is in center of mass frame. Center of mass velocity will be u by 2, so I am observing from a frame which is moving with velocity u by 2, or I am observing the entire situation from center of mass frame. Then this guy's velocity will be u by 2, this guy's velocity will be u by 2. Net momentum of the system is 0. Now, after collision, I do not know what is happening. Again, I am going by the same thing. Rod will be having some velocity v and it will be rotating about center with omega kind of thing. Motion of center and motion about center I am visualizing. But net momentum of the system will be 0 in center of mass frame. So, quickly if this is v, I can quickly put this guy also velocity is v. So, I do not have to do momentum conservation thing here. But what I should be doing is I should be doing E equals to 1. So, velocity of approach equals to velocity of separation. They are approaching with a velocity u by 2, u by 2. They are approaching with a velocity u. Velocity of approach equals to velocity of separation. Now, this point velocity is v plus L by 2 omega due to translation and due to rotation. Now, this point velocity is v. So, velocity of separation is this velocity plus this velocity, that is 2v plus L by 2 omega, right. Velocity of approach equals to velocity of separation. Now, we should be doing, anyway, I manipulated it, I got this result. So, conservation of momentum we do not have to do from center of mass frame, E equals to 1 we should be applying. Now, I got this result, but there are two unknowns, so I need to write one more equation. The other equation is going to be conservation of angular momentum. Again, I will be doing conservation of angular momentum from all the 3 points as I have done previously. So, if I take this point, angular momentum of this point is going to be 0. Angular momentum of the rod will have two components, angular momentum of center of mass and angular momentum about center of mass. About center of mass it is not rotating, so it will have only angular momentum due to center of mass, that will turn out to be L by 2. This distance is L by 2 into mu by 2. Of point mass it is 0, for rod there will be two components, of center of mass and about center of mass. Of center of mass we calculated, about center of mass is 0. Now, I have taken this direction is positive. Now, finally, angular momentum of this guy again is 0. Now, angular momentum of this guy will have two components, angular momentum of center of mass, about center of mass. Of center of mass is in this direction. We have taken this direction is positive, so of center of mass will be negative and about center of mass will be positive. Initial angular momentum of the system equals to final angular momentum of the system. point it is 0, for rod there will be 2 components, off center of mass, about center of mass. For point mass it is 0, for rod there will be 2 components, off center of mass, about center of mass. Now when I did the calculation, I ended up with this result. So I got one equation from here. I got one equation from E equals to 1, I got one equation from conservation of angular momentum. One equation from E, one equation from conservation of angular momentum. I solved it and I got omega is same as previous omega. See, even if I shift the frame, omega will be same, right? So omega of the rigid body I am getting same, but V I am getting some other thing because this is the velocity of the rod in this frame. That can be different. We will see that later, right? So omega is same, so our answer is correct. In fact, I have checked whether this will yield me previous result or not. So velocity of rod is minus u by 10, but when I shift to ground frame I should be adding u by 2 extra, so it will be 2u by 5, which is matching with the previous result. So our answer is correct. Now I will be doing conservation of angular momentum about point Q. If I do conservation of angular momentum about point Q, okay, this guy will be having L by 2 into m into u by 2, this is angular momentum of this guy. Angular momentum of this guy will have 2 components, angular momentum off center of mass and about center of mass. It is not rotating about center of mass, so it will be 0. Angular momentum off center of mass is also 0 because velocity is passing through that point. So for this guy, this is the angular momentum. For this guy, there will be 2 components, off center of mass and about center of mass. Off center of mass is also 0, about center of mass is also 0. Now finally angular momentum of this guy will be, see, I have taken this direction is positive, now this direction is negative. So angular momentum of this guy will be minus L by 2 mv. Now this guy will have 2 components again, off center of mass and about center of mass. Off center of mass is again 0. About center of mass is in this direction, which is positive for me. About center of mass IC into omega ml square by 12 into omega, right? Initial angular momentum equals to final angular momentum. Initial angular momentum of this guy plus initial angular momentum of this guy equals to final angular momentum of this guy plus final angular momentum of this guy. Initial angular momentum of this guy will have 2 components, off center of mass, about center of mass. About center of mass there is no rotation, off center of mass it is passing through that point, so it is 0. This guy will have 2 components, off center of mass and about center of mass. Off center of mass is 0 because it is passing through that point, about center of mass we calculated. So when you manipulate it, you will be getting some equation. We will be using E equals to 1 and conservation of angular momentum. E equals to 1 we got this, conservation of angular momentum we got this. I solved, I got omega value as the same thing and V value is minus u by 10. And yeah, these results are same results, so it is correct. Now we will be doing conservation of angular momentum about other point R. When I do conservation of angular momentum about the other point R, angular momentum of this guy will be L into mu by 2. Angular momentum of this guy will have 2 components, off center of mass and about center of mass. Off center of mass, see this direction, for yellow guy this direction, right? This direction I have taken positive. For white guy it will be this direction, so this direction will be negative. Angular momentum off center of mass and about center of mass it is not rotating, so 0. Now finally angular momentum of this guy minus, and angular momentum of this guy will have 2 components, angular momentum off center of mass and about center of mass. Angular momentum off center of mass is positive, about center of mass is also positive, right? Initial angular momentum of the system equals to final angular momentum of the system. Initial angular momentum of this guy plus initial angular momentum of this guy equals to final angular momentum of this guy plus final angular momentum of this guy. Initial angular momentum of this guy will have 2 components, angular momentum off center of mass and about center of mass. Final angular momentum of this guy will have 2 components, final angular momentum off center of mass and about center of mass. So when I manipulated it, I got this equation. Again I will be using E equals to 1 and this equation. E equals to 1 and this equation, again when I solve it I will be getting the same result, so that is correct. But if you notice one thing carefully, this thing I have highlighted here, that is L by 2 into mu by 2, that is L by 4 mu. Here also I am getting L by 4 mu. Here also I am getting L by 4 mu. So in center of mass frame, no matter whether I took point P or Q or R, I am getting angular momentum of the system as same. That we can generalize even, so I will show you the generalized result. So in center of mass frame, that is when the momentum of the system is 0, no matter about which point you calculate angular momentum, it is going to be same. That I will be showing you here. So in center of mass frame, that is when the momentum of the system is 0, in center of mass frame momentum of the system will be 0. So in that frame, what will happen to the angular momentum of the system? So net momentum is 0 for all the particles. If you do the summation of all the momentum, it is 0. So under this case, I need to convince you, no matter about which point you take angular momentum, it will turn out to be same. So angular momentum about point P will be given by position vector of first particle cross momentum of first particle. Position vector of first particle about point P plus momentum of first particle. Position vector of second particle about point P plus cross momentum of the second particle. So that's the summation. Now this position vector I can write it as position vector of first particle with point P plus position vector of point Q with respect to point P. That's vector summation, right? I can write this vector like this. Now I am expanding it, and this is a constant. Position vector of Q with respect to P. P is a fixed thing, Q is a fixed thing, so this is constant. So this summation I can write it as this summation, I can take it inside. Now summation of all the momentum is 0. Now if you look at this one, this is looking exactly same like this. This is position vector of first particle with respect to point P cross momentum of the first particle. That is angular momentum of the particle with respect to point P. This is angular momentum of the particle with respect to point Q. When you add all such things, you will get angular momentum of the system with respect to point P. When you add all such things, you will get angular momentum of the system about point Q. Now you can see here, if this term becomes 0, then these two will be equal. That is angular momentum about point P equals to angular momentum about point Q. When will this happen? When net momentum of the system is 0. If the net momentum of the system is 0 in some frame, then no matter about which point you will calculate angular momentum, it will turn out to be same, right? Thank you.